purpose of this video is to walk through the various tools that we're using in Lab 6 and to demonstrate a few things, particularly with respect to symbology that you might find useful in the lab practical, as well as in assignment 6. Now, I talked through what's going on in this assignment in the voice thread, but I just want to mention that the basic idea here is we're looking at continuous level measures. That it means measures that are numeric and that allow us to look at relationships, the likes of which we've been discussing in the last couple of voice threads. So we have soil pH, and we also have these three measures of soil content, the three components of the soil. The sum of these three numbers should be 100. It is in most cases in this sample that we're looking at here, but it's distinctly not in a couple. Looks like Team 7 and Team 9. Now, this is from last fall. I'm not calling out anybody from this semester. Got it kind of wrong, but make sure when you're entering these values that they sum to 100. And you're going to create your own sum so that you can eventually calculate the percentages, and you'll see there are three double fields here for percent silt, percent clay, and percent sand that I've added. You're going to do the same thing. And the formula for that is just each of these components divided by total, which should be 100. The other thing you've got from the field is soil infiltration rates. That's in seconds. And soil pH, in this case, I'm not quite sure why. I had some trouble with it. Don't remember. But anyway, I copied it over as pH, which I'm using in my examples in the voice thread and here. Now, the first thing you're doing in this lab is just taking a look at the patterns that you see. And I think it's a lot easier to see those if you modify the symbology. So here, rather than, why does this keep going back? Here we go. Rather than a single symbol like we're looking at in this example, I'm going to use graduated colors. Now, those are harder to see at first, and I'm going to change the ramp to something a little brighter, like yellow to red. They're still a little hard to see. So if I change the size of those symbols, I can go here and say format all symbols and change this to, like, I don't know, 7 or 8. Then they're a little easier to see, and you can see that they're on a color ramp. Now, if I wanted to add to that, if I wanted to improve on that, I can then click on this vary symbology by attribute and also change them by size using pH as well. And then it gets, in this case, I'm using soil pH, I guess. And then it gets a little easier to see the differences. Of course, that's pretty profound. So I'll knock that down a little bit, 24 point. And then you can see through color and through size the differentiation of our measurements. And you can ask yourself, does it look like this bears any relationship to anything else? What you know about campus, like there's this stream running right through here. Looks like our higher pHs tend to be somewhat correlated with proximity to that stream, not entirely. So the most distant points, if they were truly correlated, would be the smallest yellowest. It's not entirely true, but maybe distance from that stream is something worth considering. We don't have that measurement. I should get y'all to create it. But if I turn off the base map and turn on the slope raster that I've given you, I can see if they bear some relation to slope, and it's really hard to say they do. One thing I didn't mention in this raster that you yourself are calculating is the slope. And just so you can see how that operation works, I've already derived it in this file that I'm showing you. But if you go into toolboxes and under Spatial Analyst Tools, you'll see map. Extraction, and you'll see extract values to points. Actually, extract multi-values to points. This tool basically is just what it sounds like. What you're doing is you're feeding into it a set of points, and you're putting those essentially on top of a raster. In this case, the raster that we're looking at is a slope raster. And that means that at each cell, it's telling you the slope. Higher numbers mean steeper locations. You can kind of see how that corresponds to the map. And so here what we're going to do is name the output slope. And when you run it, it will add a column to your attribute table. So it's just spearing the cell beneath each point and putting the value of that cell at that point within the attribute table. Pretty cool function. So that's how you derive the slope. Then when I say run, that will create that field. I've already done it in my case, don't need to do it again. And so what I'm having you do at the beginning of the lab, once you've put together the data table and you've got the correct measures and you've calculated total soil and these percentages, then what I'm asking you to do is just explore what you've got a little bit. It really helps to differentiate things. So rather than soil infiltration, I can switch that to clay content and see what those numbers look like when I look at the percentage clay instead of something else, instead of pH. And so I can run through the various measures and take a look at them. The other thing I do at the same time is take a look at the descriptive statistics. And to do that, I go to a measure, right-click on it, and say statistics. That gives me a distribution, in this case, a weird-looking distribution. What am I looking at? So in addition to looking at the spatial properties, and I also think it's good to look at those spatial properties while not looking at anything else. So looking at those properties without anything else turned on. I think it's also, the other thing I show you how to do and suggest that you do is take a look at the actual summary statistics of that same measure. So in this case, we're looking at the distribution of pH across the various samples that were taken by this cohort last fall. And I just want to show you a couple things about this. When you're looking at this chart, you can modify several things, and it's helpful to get to know it a little bit. For starters, you can change the color of these bins under the data location just by changing the color. But more importantly, what we're going to look at and assess is the shape of this distribution. We see that the high point is at relatively acidic levels, so in the 5.8 to 6.1 range, so it's fairly acid. The average is a little higher than that, so that tells us that we do have a lot of values above that high point. It's not exactly a normal distribution, but it's got normal-ish qualities. It's got a single mode and things taper in either direction from that mode, not uniformly. But it's not exactly a skewed distribution either. And so these things are really helpful to keep in mind when you're looking at the each of the various measures in the data set. It's helpful to bear in mind the median, the mean, and the standard deviation. The standard deviation is telling us that the values tend to cluster pretty close to the mean. There's not a huge range, and we kind of see that because it only ranges from 5.2 to 7.5. And what I have you do then is look at the descriptive statistics for this measure, and you're going to actually report it for a couple measures, but more importantly, look at it for all of them, just to get a sense of how they range spatially, where they seem to be alike, where they seem to be different, because exploring your data gives you insight into what those data can tell you. The other thing I suggest is looking at them in isolation. But once you've taken a look at the data individually or univariately, then what I have you do is take a look at them with more than one at a time. So multivariate analysis, in this case bivariate, looking at two measures at once. And so what we're going to generate is a scatter plot in which we look at slope and pH. So I'm going to find that slope measure. I just showed you how to derive that. And I'm going to make it be X, actually. So I'm going to say, is the acidity of the soil somehow attributable to pH? For whatever reason, this doesn't show up until I undock it. I'm not quite sure why. But you can see here, what we're looking at each point is the intersection of those two values. So we have one sample location where the slope is really not steep, less than 3, about 2, and the pH is 5.2. And this location over here is a spot where it's considerably or relatively steeper, like a slope of 21, and the pH looks like it's about 7.3. Now what we're asking here, is this somehow a systematic relationship? Does it look like this is an undifferentiated cloud where there looks to be no relationship between these two? Or does it look like something is happening here, that there's some sort of dependency between slope and pH? Now we might have a body of theory that we're bringing to bear on this that would influence our opinion or our answer to that question. But as uninformed soil scientist, I'm just looking at this and saying, well, okay, I can say that's a relationship, but it's a pretty faint one. There's a lot of noise. Now we measure noise in terms of statistical error, which we measure as how far is it from each point to that line, square the distances and add them together. This line is called the linear trend or the regression line. It's the line that minimizes the overall distance of each point to it. There is no line that fits these points better. And we measure better, again, by taking each point, how far is it from the line, square the distances, and add them together. Now, in this case, this line, if you think about what we talked about in correlation is basically saying to what extent do these points form a line? And not really. They're all pretty far from it, or a lot of them are. And so it's hard to say that this is a tight linear relationship. In fact, the correlation, which is the square root of r squared here, think about what the square root is. It's tiny, less than 1%, meaning about 99% of the variability in pH is not attributable to the slope of the land nearby. So this is a weak relationship, but to the extent there is a relationship, the linear trend, this algebraic equation right here, which is, I say algebraic because it's what you learned in algebra, y equals the intercept plus the slope times x. And if you feed in any value of x and multiply it by 0.01 and add 6.2 to it, that'll be your prediction for pH. It's worth noting that no pH in this model can be predicted from our data that is below 6.2, because the formula is saying regardless of the level of 8x, the estimate is going to be higher than 6.2. So there's a lot of error in the prediction, but the important thing here is the slope is saying what happens to our prediction of y for every unit change in x. So if x goes from 5 to 6 or from 9 to 10, y, our prediction of y, goes up 0.01. Well, 0.0114, but let's round it to 0.01. So 1/100th of a unit of y. So not much. So this is a weak linear relationship. But that's how we read these things. And this allows us to ask the question, does there seem to be some sort of relationship between x and y? Correlation can help us answer the question, is there some sort of linear relationship between them? There might be a nonlinear relationship that correlation doesn't see. And to the extent there is a linear relationship, regression allows us to say, what is the effect that x is having on y? And that effect is the slope, 0.01.